So good afternoon and happy Friday. Please excuse ahead of time my voice and sniffles. There's wintertime stuff going around. So today the plan is to get you started with project number 3. I thought I was going to get it posted last night. I posted it this morning. It's been a whirlwind last 24 hours between meetings and other stuff that has been vying for my time. So why don't we get started first? How's everybody doing? Good. Glad it's Friday. I guess we're supposed to be getting some more snow, right? So, unfortunately, if you're a snow lover, then I guess that's good for you. All right, why don't we jump right in? So, when we talked about adversarial search, we mentioned the term utility, and we said one of the approaches that you can use to compute utility is to look at certain aspects or features, as it were, of the state. What features are indicative of winning the notional game, that terminal state you reach would be a win. And so we're going to take a look at that, both in terms of the theoretical consideration in Pac-Man, but we're also going to look at that from a practical standpoint in the context of the evaluation function for the reflex agent, okay, to get you started. And then after that, we're going to look at the support routines for MINIMAX search to also get you started towards project number 3. And so I haven't set up the backend environment yet for Gradescope. So if you're really eager and you're ready to submit it by this evening, Gradescope backend should just about be ready. If you're curious, there's a bunch of custom scripts that you have to develop, and you log into a virtualized server instance with a container installation and blah, 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 right? So there's a bunch of other stuff that happens behind the scenes in support of AutoGrader. But nonetheless, when we talked about so-called material value, we looked at it in class in the context of chess, right? So I'd like to go over with you an example of that same idea, material value, features associated with states for the Pac-Man game that are conducive or indicative to reaching a terminal state that results in a win, meaning Pac-Man clears all the food. Now, in this environment, as we adversarial. And so when Pac-Man moves, Pac-Man can't just move. Well, Pac-Man could, but Pac-Man has to be aware of the actions of these adversaries. Because if Pac-Man comes into contact, excuse me, with one of the ghosts, then the game is over, right? So the actions of the ghost go directly against the goals of the Pac-Man agent. And so with this, in the implementation, the agents are ordered by their so-called agent index, and Pac-Man is always so-called agent 0, right? And so all the subsequent agents, agent 1, agent 2, and so forth, index through the ghosts. So if you have one ghost only, and you can control that with command line options when you run the environment, you can have as many ghosts as you choose. I mean, granted, if you had enough ghosts to have one ghost for every pellet, that would be a little bit difficult, but nonetheless, it doesn't appear that there are limitations beyond the max integer value. But nonetheless, if you have more than one ghost, then you'd count from agent 1 from the agent index of 1 for the first ghost, agent index of 2 for the second ghost, and so forth. And so that matters in when you construct your MINIMAX search, your game trees. Recall that after the max node gets a try, that's going to be agent 0, namely Pac-Man, all of the other agents are going to get apply, right? So you're going to have a much deeper MINIMAX game tree as you increase the number of ghosts. Okay, so let me put the question, excuse me, out to all of you. Let's think about this idea of desirable features, or just to be more casual, desirable attributes associated with game state. And so to jar your memories, let's think first, excuse me, about what game state is. What is state? I shouldn't use the term game state because that has a meaning in the code base. What is state? What aspects of the environment are relevant to the representation of this environment relative to your playing the game? What's relevant here? Colton? The the walls. Okay, so we said the walls. And what do the walls do? How do the walls influence the game? How do you think? Yes, Colton? Well, you cannot move. Okay, so you have your actions, which you can call for each state. And theoretically, I'll just say, I don't know how to say theoretically equal to, right? That's not such a thing. But nonetheless, you can go north, south, east, or west. But because of those walls, you might be selecting some set of actions that is a subset of north, south, east, and west. Okay. So the walls are important. Is there anything else that might be relevant to Pac-Man playing the game? Because yes, the walls are relevant because that shapes the legal actions you can take in each state. Any other thoughts? Yes, Zion. The food pellets. So we have the food pellets. And what about the food pellets? Could you say that last part? The score that you have and what? How close you want to complete the level. How close you are to completing the level. So the food, yes, does determine the score. For each tick that transpires, you subtract a point, and for each pellet that you eat, it is it's plus 10 points, right? So yes, it absolutely does. And it also determines whether or not you clear the level. And so how do you clear the level? What do you have to do to clear the level? You eat all the pellets. So you have to eat all the pellets. Well, that should be an E. And that means you have to come into contact with each pellet. Pac-Man has to occupy the same space in order to eat the pellet. So that means there's some relationship between Pac-Man and the pellets, and let's call it the eat status for each pellet matters. And so either each pellet is eaten or each pellet is not eaten. And so we know we have our walls, we have our eat status for the pellets. Okay. In this adversarial environment, is there anything else that might be an attribute or descriptor of a state that encodes this notion of conducive to winning, right? So what about this environment, or what aspects of the environment might be conducive or more conducive to Pac-Man winning versus Pac-Man losing? Any other thoughts, brainstorms, Alexander? The ghost locations. So the ghost locations. Okay. So what about those ghost locations? Where they are in relationships. So the relation, Leon? Okay. So if they're in the same position, so is it only, so let's say the relationship and we'll say position. So let's say if we have Pac-Man here, Elliot?
So it's also relevant where they can go to, right? Like not just the current location, but like, for example, if you are trying to figure out whether you can put the add that in the corner, you need to know whether the ghost will reach that corner before it.
I see. So the relative position projecting out forward in time.
Right.
And
Also,
they do, absolutely. And that's look ahead, right? That's a different type of agent, and that's absolutely an excellent approach, right? But at this level, let's only consider the snapshot that we have right now, right? And you would absolutely look ahead in, if you were entering a game playing agent contest, you want to project forward to evaluate those contingencies. Absolutely. Um, let's pose a scenario here. Let's say in frame one, we have, Pac-Man here, and we have a ghost here. All right, there's my cartooning class helping me out. And then let's say we have another frame. We'll draw it over here. Now just imagine it's the same size. And again, we have Pac-Man here, but we have the ghost here. Which is a quote unquote better scenario? Scenario on the left, we'll call that A, or the scenario on the right, we'll call that B. Which is better? Um, I don't. Alex. Oh, and I said Alex in my brain. Alex or Alex. I know your last name, but it's just like for some reason. Alex. A is better. Why is A better? B is better. Why is B better? You want the ghost to be far away from them. So we have these notions of attributes or descriptors or features that you don't know for sure if it's good, but these qualities generally mean Pac-Man eventually will find paths that are wins. So you want to eat the food. And to eat the food, you have to be closer to the food, right? So if you were going to take one of two moves, one that would take you further away from the food, one that would take you closer to the food, which would be more desirable? Not a trick question. Vincent, closer to the food. And so closer to the food, but what happens then, for example, in scenario B, you can move closer to the food, but in moving closer to the food, imagine there was a ghost there. That's my ghost over the food, right? Would that still be a good move to do? And so whenever you design this notion of an evaluation, that evaluation should somehow count these descriptors, and there are many descriptors you can have. And these descriptors, if the idea is to pursue that state that has the highest evaluation, it should either reward, meaning return a big value for something desirable, or penalize, return a small value for something that's not desirable. And so let me ask you, if we had, excuse me, this notion of distance to ghost, is a bigger value for that or a smaller value for that? Should that say better, right? If bigger means better utility. Any thoughts? I can see passes something well. Alexander? More distance is better. Okay. So that means if we had some quantity that represents distance to the ghost, if we were designing an evaluation, if it were going to count somehow distance to ghost, we want, when that distance is bigger, that contribution to the utility or the evaluation is going to be bigger. Okay. What about the food pellets? If we had some notion of closest food pellet, should we reward for that being bigger or smaller in its contribution to the notion of a desirable state utility? Any thoughts? No? Chris? Distance space. Okay. So if we want that distance, right, we want that contribution to the score or to the evaluation to be bigger when it's closer to the pellet. Well, we might want 1 over the reciprocal closest pellet, or some scalar, we'll just say, well, let's not use A, some scalar, not B, this branching factor, some scalar, no, S is state. Um, I don't know, let's just say A, right? Some scalar A, but that feature we'd have in the denominator because we want this contribution to be larger, i.e. larger utility if we're closer to the pellet versus if we're further away. Does that make sense? And so whatever features that you implement or you employ when you're implementing your evaluation function or utility function, each one of these features makes a contribution, and how you put these contributions together, it's entirely up to you. You could have the ratio between two features. You could have a scalar times two features. You could have the product of features. It doesn't really matter. What matters is that it's rewarding correctly so that you get a higher evaluation for a more desirable scenario. Chris? We're not considering power pellets for the season. But if you were considering power pellets, that would certainly be of high value because you're also changing the role of what happens when Pac-Man collides with the ghost. Keeping in mind that it's only for a notional season, right? It's on a time. But yes, absolutely. If you had the full Pac-Man game and have people peeking in the window, outside the classroom, that always creeps me out. You know, just some history. But anyways, if you had the full game where you're considering power pellets, absolutely. You would include in your evaluation function some feature that contributes a value that's high when you're near a power pellet. And the ghosts are scared, right? You can include that also, keeping in mind that that's on a time. So you could have 4 terms. One term would be power pellet, right? How close you are to the power pellet. And you reward very high values for that contribution when you're close to the power pellet. And then once you've eaten a power pellet, then you would turn off that distance to the ghost, or maybe say 1/over distance to the ghost. So if you want to get closer to the ghost for that period of time when the ghost is scared straight after you eat the power pellet. So absolutely, you can include all of those things. And so really think and, tinker with this. Don't spend a ton of time, but tinker with how these things impact behavior in Pac-Man environment as you turn on, turn off, tinker with various equations and contributions for different features. Does that make sense? All right, and that's essentially the first question on project number 3. And we'll tinker with this in real time. Okay. And so when we talked about a MINIMAX search, we said that you alternate between Max's action and Min's action, and Max picks the biggest of the choice of its successors. It picks the biggest of the Min choice, and Min picks the smallest of the Max choice. And so it looks like a depth-first search. And when we return, it's Max considering all of the potential moves of its adversaries. And so in the case of Pac-Man, in the general case, if you have just one ghost, it's just Max and Min. If you have more than one ghost, it's Max and Min 1 for the first ghost, Min 2 for the second ghost, Min 3 for the third ghost. And then it's Max's turn. Does that make sense? All right. So one of the first things you should do for MINIMAX, mirroring the pseudocode, you should write some utility routines. And these routines, as we've covered, is toMove to determine which player's turn it is, actions, results, the transition model, is terminal, the check the terminal state, and utility. Now, of course, because of how the environment is implemented, for some of these routines, you're going to need a parameter for the agent index, right? Because the agent index is passed to you, and that's how you know which particular agent, be it Pac-Man, Ghost 1, Ghost 2, Ghost 3, etc., whose action is going to be, okay? So that's something certainly to keep in mind. Any questions? No? All right. So why don't we, and we're going to spend most of our time on the first aspect, and then we're going to spend whatever time we have left on some of these routines and considerations for some of these support routines for MINIMAX search. Okay. So let me, um, so share is up. I already have PyCharm going, and my laptop is like overheating. I don't know why. You can hear the fan. I'm going to share my desktop. I have do not disturb on it. I always get spam phone calls and stuff, only when I teach, when I'm in meetings for some strange reason. But nonetheless, I have the project code up in PyCharm, and I'm just going to first walk you through the first uh, the first part. I have some notes here. Uh, okay. So if you wanted to play Pac-Man, you just run Python Pac-Man, and it defaults to the keyboard agent, and it allows you to use your arrow keys, which isn't very effective. Joystick is better to control the game. And so you can just play, get a sense of it. Power pellets work. Oops, I'm better with the joystick than the console. But anyways, so once you've run that, the next thing to do is to take a look at the reflex agent. Now, the reflex agent makes its choices based solely on the score, and we can take a look at that code. So running Python, pacman.py, reflex agent on what's called the test classic board. So let's go ahead and run that. This is the test classic board. It's very simplified. It doesn't have walls, and it's just a quicker test of your your Pac-Man algorithm. You can run it on the classic maze. Let me see. Helps me to remember. Okay. What's it called? Simple classic? Nope. Original classic. There we go. All right. And this is the reflex agent on Original Classic. And you can see it's not always making optimal moves. It's based entirely on the score. And you'll see sometimes it pauses and it sometimes runs into the ghosts, right? Not very effective. If we take a look at the place where all of your code is going to go, inside of multi-agent, there's reflex agent, and inside of reflex agent, we're going to look at the evaluation function. So here, the evaluation function, it has a bunch of calls to inspect various data structures. It has a bunch of calls, and it's recommended you use these calls to inspect the data structures. There's no better thing than to ask the runtime what things are and how they fit together. In fact, I highly encourage you to set a breakpoint in the main entry point for pacman.py and just walk through and see for yourself of the entry point from the game environment into your reflex agent, as well as the role that the evaluation function plays when you're trying to make a determination over what is the best action and therefore successor to pursue. And as you can see in your evaluation function, here, it just says successor game state get score. And so you start out with some number of points. For each tick of the clock, it deducts a point. For each pellet that you eat, it adds 10 points. And you can see, particularly, let me go back here. For the test classic, it doesn't always make reasonable moves. Sometimes it pauses, sometimes it goes into the ghost. Now, granted, the default ghost in the test is a so-called random movement ghost, right? And by nature of random, it sort of violates the working assumption for adversarial search. It's a zero-sum game, meaning that it's supposed to act to maximize its goals, right? So it should act perfectly against Pac-Man, but the ghost is making suboptimal move because it's choosing a direction to move randomly instead of trying to minimize. Okay. But nonetheless, let's try to add some features, so-called material costs, that describe aspects of the environment that are conducive to a winning evaluation, a winning terminal state. And so we alluded to this idea of distance to the ghost. Now, of course, that feature, distance to the ghost, that's not the same as getting all the pellets. So what we're going to do is we're going to try distance to the ghost, observe its behavior, and it'll avoid the ghosts, but it's not going to be as concerned, really not at all, about trying to clear the board, right? Those are two separate features. So let's go ahead and let's type min ghost distance, and we're going to initialize that to infinity. And then we're going to iterate. Let's see, what did it get? It got new ghost state. So, okay, ghost state in new ghost. I hate this autocomplete thing. So let's get ghost position, and we're going to say ghost state, get position. And then from that, we're going to say its distance, util Manhattan distance. And we're going to take the Manhattan distance between new position, which is the Pac-Man position calculated above, and the ghost position. Okay. So we're just going to iterate through these and we're going to pick out the min. Yeah, I could do it in one line, but it's easier to have the narrative while I do it this way. So I'm going to say if ghost distance less than min ghost distance, then I'm going to say min ghost distance gets ghost distance. Okay. I'm also going to concurrently do something else, something I call the boo factor, right? And what the boo factor is, it's just going to add up all of the ghost distances alongside, since I'm in the iteration anyways, it's going to add them up alongside extracting the min ghost distance. So I'm just going to say boo factor plus equals ghost distance. Okay. Now, of course, in the single ghost case, it's trivial, right? It's just the same as the min ghost distance because it's just one ghost. But in the multi-ghost case, it would matter more. Okay. So now we're going to come down here and let's decide first to keep the score component and then just have only that min ghost distance. And we'll see how having just the score, which we saw, versus just the min ghost distance versus some combination, let's just use the sum of the ghost distance and the score, right? Because score conceivably is, you're wanting to get more pellets, okay? So let's see how that behaves. So I like saying result equals, let's just say min ghost distance. And let's just have another one, result equals min ghost distance plus successor game state. I'm just going to comment out one, get score. Okay. So let's just try the version that's just the min ghost distance. So return result. Result. Okay. So let me save this. Let me hide these controls and let me file, save all. Okay. And I'm going to go to the command line again, just so you can see that visualization. on the test classic, and we'll see how that fares. Oops. Get position. Oh, if I spelled it right. Um, Postion, position. Okay, so let's see. Save all. That's the problem with computers. They do exactly what you tell them to. G host. Oh boy. Um, G host. G GHOST. What did it? Oh, thank you. All right. Seeing if you're paying attention. No, that's a typo. All right. Thank you. All right. So let's save this and let's try this again. Clear the terminal. Let's take a look. So it's avoiding the ghost. It is doing a great job, but look at what happens to the score. The score is just decrementing and decrementing, like a juke in football, right? So it's doing its thing. That's just looking at the nearest ghost. It's doing a great job, right? But at the end of the day, our score isn't what it should be, right? We're burning a lot of time moving, but not making progress and clearing the board. Okay. So let's try turning on that contribution for the score. So now we're going to use the score as well as the distance from the nearest ghost. So let's try that. It's not as frantic, but it's still, because it's such a narrow passageway, it's still, you know, more so. Oh, there we go. Ooh, that was a good interaction. More so avoiding the ghost. There we go. So it was marginally better. Okay. So let's open this up for the original classic and see what happens. Okay. And this is actually, you know what? Let's try out just avoiding the ghost first with the original classic. So let me turn that back on because we saw what happened with the score. And save all. And let's see what happens with just looking at distance from the ghost, min ghost distance in our evaluation. So it's not doing anything because there's no existential threat, so to speak. And in this case, we have 4 ghosts. So there is a min ghost distance. So now it gets pushed along whenever a ghost is quote unquote close enough. But when they're far, it was too far to really make a difference, right? Okay. So again, we're taking a long time, but once the ghosts are pursuing, and these ghosts kind of pursue, Pac-Man, to humanize it, becomes complacent and isn't so interested in getting pellets. So Pac-Man, almost like a repulsive magnetic force, right, is being pushed along by the ghosts. Okay, so let's kill that. Now let's see what happens with that maze if we bring in that feature that says count the score, right? So scores that are smaller are preferred less, those states, to scores that are larger. So conceivably, theoretically, it should be encouraged more to pursue the pellets because that increases your score. So let's see what happens with the original classic maze. It's doing a little better. It's not sitting idle. It's actually navigating the maze to pursue pellets, but not always. But certainly better than just using ghost distance alone. Okay. So let's give it a little bit more time and see how it does. Can we clear the board? Get stuck. Ooh, oh man, that was nervous. All right, nerve-wracking. So it just sits idle until the ghosts come near enough. let's see. Let's kill this. All right. So min ghost distance. Oh, wait a minute. That means if the ghosts are far, it's better. If the ghosts are near, it's worse. So we want something else beside the min ghost distance. Well, actually, rather, no, that's true. We want the distance to the smallest ghost to be bigger. So you want to be further away from the ghost. So I misspoke. Okay, so let's bring in some aspects of the food pellets. Okay, first, any questions? No questions? No. All right. So let's look at the distance to the food pellets. And I'm going to do min finding in this example and look at the distance to the closest food pellet because I know that the time it takes to move is going to decrement from the score. I want to pursue this notion of the closest food pellet. So I'm going to go in and, oops, excuse me. I'm going to go in and I'm going to say food list is gets new food, which is up above, as list. And when you do this, it's going to iterate through all of the food. And for each food pellet that's a true, it's going to return its XY coordinate. Okay. So these are going to be all of the uneaten food pellets. Okay. So now I'm going to say the number of uneaten, no, not number of uneaten. I'm going to say I jumped ahead. Min food distance is equal to float infinity to seed that for food XY in food list. I'm going to take the distance as the util Manhattan distance between new position, which is Pac-Man's position from up above, to food XY. Okay. Oops. XY. So then I'm going to say if the distance is less than min food dist, I'm going to say min food dist gets dist. I almost typed a semicolon. That's like burned into my soul. Gets dist, and then I'm going to say closest food is food XY. And I'm going to set closest food um, uh, okay, I don't need that really. So I'm just gonna closest food, none, just for good measure. All right. Don't know if I'll need it later. So now I'm gonna say, minimize ghost distance. If I'm further from the ghost, that's a good thing. I want to maximize the score, so bigger scores. That's a good thing. And I want, let's say the reciprocal, plus 1 upon min food dist. And I'm going to add a fudge factor plus 1 because you don't want infinite, right? Just in case. So now we're going to, let's do this. I'm going to copy this line and I'm going to have different versions of things. So this is the consolidated version. And I'm going to just use min food dist, 1 upon min food dist, as my singular criteria feature, and I'm going to see how it does. Okay. Now, of course, well, scores can be big, but let's just try this min food dist. Let's see what happens. So if the food is closer, this quantity is bigger. I could certainly scale it up by making the scalar in the numerator bigger, right? But let's just try this and see what happens, both in the test maze as well as in the classic maze, and look at how that shapes the behavior. Okay, so that's original classic. It's test classic. So let's see how it does. It doesn't really do anything because that contribution is probably too small to make a difference. So let's go back then and let's blow that up a little bit. Let's make it 10 upon that min food dist. So let's save it and let's see if that makes a difference, because the score was overwhelming those values. If the food distance was 5, it'd be 1 upon 6. And 1 upon 6 is so much smaller than the 10 points you get for a pellet or just even the score, right? So let's try that and see what happens. So we're going to scale that up in its value. And let's try the test classic maze and see what happens. It moves a little bit. It's not very effective. Okay. So let's do something different. Let's bring in both the min food dist and the min distance to ghost. But this time, we're going to say min ghost dist over the min food dist, right? If they're equal to one another, well, it's roughly 1. If they're not equal, then maximizing the distance to the ghost is going to give us a bigger score while we pursue pellets. So let's try that and see what happens. Okay, so let's try it on the test maze. And it doesn't really give us anything. Oh, that distance to the ghost pushed us along, but it's not strong enough to pursue the pellets on its own. So we do need that score, right? Okay, any questions? No? So let's try this. Let's bring back in that score, successor game state get score. And let's see how that works, because we know as the score changes, and I probably misspelled it, 2C's, Success. And let's see how that combination affords us improvements potentially on our performance. So let's run test classic. Oh, wait a minute. The score is important. We're avoiding the ghost, and we're also pursuing those packets to try to make sure our score is as big as possible. Because consuming a packet adds 10 points. I'm packet. Thinking consuming a pellet adds 10 points, but having time transpire deducts 1 point, right? So it's going to prefer actions that lead to that plus 10. Okay, so we're somewhere. So let's see in the big bad world of the original classic to see how well that scheme performs. Okay, so we try that out. We're pursuing packets, pellets. Okay, I keep saying packets. I don't know why. Um, and then we get stuck until a ghost comes along and sort of pushes us along. Okay, it seems like it's doing okay until we get stuck again because that contribution from the ghost is not really making much of a difference. Okay, so we need something else. We need some other feature that's going to tell us some notion of this idea of it's important to keep clearing the pellets as time transpires. Okay. Any questions? No? No questions? All right. So we know cumulatively, it's kind of nice to um, to eat as many pellets as possible. And eating as many pellets as possible is the same as saying how many pellets are uneaten. Only if the number of pellets that are uneaten is large, we want to penalize for that. We want to make it smaller. If the number of pellets eaten is small, we want to reward for that. We want it to be larger. Okay. So I'm going to take this food list and I'm going to say num uneaten uneaten is equal to the length of the food list. Okay. And so again, when you say as list for each entry that's uneaten true, it returns back its XY coordinate. And so the count of those tuples inside of the food list is going to be the number of uneaten pellets. Okay. All right. Any questions? No? All right. So now let's add that in. Well, we're not going to add it. Let's include it, poor choice of words. And let's say minus num uneaten uneaten pellets. I mean num uneaten. Num uneaten. If I spelled that right. There we go, minus num uneaten. So this version of our evaluation, it's going to reward for being far away from the ghosts. It's going to be rewarding for being close to pellets. I get to your question, Vincent, in a second. It's going to reward for having more eaten pellets, and it's going to reward for actions that increase the score. Your question? I'm having a hard time hearing it. We'll see. Let's try it out. This is walking you through an exploration of thinking about features that you could extract from state descriptions, not about solving the problem for you. That's your job, okay? Um, so let's just take a look, because you can have many descriptors of your environment. Some are very specific, the closest particular thing. Some are more general. How many pellets are uneaten? And so, as many features as you can come up with, the more descriptiveness you have about a state that you believe would lead to a terminal state that reflects a win for the max agent, the better, right? So, there's no one correct way to do this. It's taking a look at how those features translate to conditions for success, right? What is utility, right? What aspects or attributes of the environment are conducive to a terminal state, reflecting a win. Okay. And so you could go over a space of literally 100 different features if you chose to. And so what I'm purposing to do here is to show everybody how certain aspects of the environment translate to differences in behavior, right? That's my goal here today. But it's up to all of you to figure out features. Okay. All right. So let's save all and let's look back through the original classic and let's take a look. So we see it behaving a little differently. Let's see what happens when we get in the corner. It's not pausing. So there was value, and now it is pausing. There was some value to that contribution. And if you wanted to really experiment with these, you could have a printout each time you evaluate to look at the value of each one of these features to see how that reward plays, and then scale them up or down depending on the amount of contribution you want each one to have for the score. You can have dynamic things, like Chris was alluding to before. If you included things about the pellet, then the role of proximity to the ghost changes if you're in this scared period that you get once you eat a pellet. But here, we see it's doing better than it was before, but it's not doing as well as it perhaps could be doing in this particular maze. So let's go ahead and let's add something that's a little bit more aggregate and see what happens in this multi-agent environment where we have 4 ghosts. Now, it would be different with 1 ghost versus 4 ghosts, but with 4 ghosts, it's not just the relationship to the closest ghost. Maybe something about the relationship to all of the ghosts might carry more information, which it absolutely does. You could, and I'm going to turn on the boo factor, right, which just adds the distances between the Pac-Man and all of the ghosts. But you could do something like compute a convex hull. And given that convex hull, you project the Pac-Man's location onto the convex hull and ask yourself, is this Pac-Man in the envelope of the convex hull that envelops all of the ghosts? That's more sophisticated. Would that work? Absolutely, because that would take care of the pathological case where Pac-Man is cornered on all sides. And maybe that's important to being conducive to reaching a terminal state where Pac-Man wins. Okay. So that's just to show you that there's no one way to do this, but this is thinking deeply about what state is and the conditions or attributes of state that you believe will contribute to Pac-Man reaching a terminal state where it wins. So let's do that. And let's turn on the boo factor. And just to remind you, the boo factor was just the sum of all the Manhattan distances between Pac-Man and the ghosts. So let's say boo factor plus, and let's see how that works. This, hopefully, should encourage Pac-Man to take moves where it's not cornered by ghosts. The convex hull method would be a little bit better. So let's take a look at how this plays out. So the boo factor is getting a little bigger. It's habituating. Oh, did not help us because it was the sum, right? You want one over the boo factor because you're summing them all together, whereas the minimum, you want to be a greater distance from that. So that didn't help us very much. So you can have all sorts of um, features, material costs, and combine them in certain ways. You can have linear combinations, nonlinear combinations, ratios, proportions, all sorts of things. Now that's on the original classic maze, but certainly if we were to run this, we'll see how we do. Oh, Python. Python autograder. Sorry. And I'm not going to run through all of them. This is just showing you the visualization of all the test mazes that it runs you through. It runs you through 10 of them, and you can turn off the graphics so that it runs faster, all sorts of things. But this is just to show you the thought process of coming up with different features. And the better the feature or set of features, the more effective it'll be for the reflex agent. Alexander? No, it doesn't. It doesn't. It's a power pellet. And so in the algorithm, the scoring rules, it's the counter decrements and then each pellet is 10. Um, it still, makes the ghost scared. Okay, any other questions? No? So please tinker with it. Be creative. Don't spend a ton. I just mentioned a ton of time. I just mentioned convex hull, but I'd rather you start on the other stuff than spend all your time on convex hull and stuff like that. That was just an example of this notion of being cornered or penned in, hemmed in by the ghosts. Now, of course, that only works with more than one ghost, right? And not with just one ghost. Okay. Any questions? So this start thinking about state and this notion of utility, and as we called it in class, material costs, those attributes or descriptors of state that you believe are conducive to reaching a terminal state for the max player, that means a win. And it's going to be piecewise, and how you combine them is entirely up to you, right? I did a ratio, I tried to sum, and then keep in mind about how you want it to reward towards its contribution to utility. Bigger utility is better, right? So sometimes that might mean reciprocation of your feature. Sometimes it might mean scaling up or scaling down, and so forth. Any questions? No? Is this helpful? All right. So let's look time that remains. And we'll do some of this along the way on Tuesday and next week, Thursday, to help with the Minimax and Expectamax. We'll be talking about Expectamax on Tuesday. Okay. All right. So next question about Minimax search. And a place to start for Minimax search goes back to the theory, right? It's a good idea to have some helper routines. So these helper routines make it easier for you to implement, and I'd recommend implementing the recursive version of Minimax. Could you do it iteratively? Yeah, you could, but it's a lot easier to think about the recursive version. And so here, again, inside of multi-agents, we have Minimax agent, which is the entry point. and your code goes in get action. And so with that, there are a bunch of helper routines that we looked at in the book for the pseudocode. And I'm going to refer back to my notes here. To move, it's inside MINIMAX agent. Let me put it inside. Um, to move, and to move was going to tell you, given the state, and we'll throw in the agent index, whose move is it? Is it min's move or is it max's move, right? So you're going to have game state as a parameter, and then you're also going to have agent index as a parameter. Now, of course, in the pseudocode, it just says to move, right? But in the real implementation, you're still going to need the agent index so you can tell whether it's min or whether it's max. And so you're just going to return here an encoding if your agent is 0, return max, that's the Pac-Man, else, fairly straightforward, return min. Okay, so that was pretty straightforward. What did I do here? Return, I didn't like something I did. Oh, semicolon, me and the semicolons. All right, so that was to move. And in addition to move, we wanted to check to see if we have a terminal node, right? So it'd be good to define a method to check to see if we're in a terminal state. Is terminal state. So terminal, if I spell that correctly. Oh, I hate this. We're gonna get game state, and we're also gonna get a depth because we want to know for a particular depth if we're at a terminal state. Okay. So what we're gonna do, set result. I always like having entry points and well-defined exit points, seasoned to taste. And then here we're going to check to see if either depth or if game state is a winning configuration, or if game state is a losing configuration. All right. And then we're going to return results. If. Oh, yeah. Let's complete this. All right. So then in kind, after is terminal, some of the other nodes, helper routines, is result, right? Remember, result took state and an action and returns the next state. And in this case, our next state is going to be the result of calling successor on game state, right? So we're building all of these helper routines that we showed from the pseudocode in the slides, and you're using those helper routines to implement that same pseudocode algorithm for MINIMAX that we saw in the book. So help yourself by using those helper routines, building up those helper routines, and then it's just literally a translation of the pseudocode directly, assuming the recursive method. If you do iterative, yeah, you could do MINIMAX iterative. It's a little bit more moving parts, a little bit more difficult to understand, but it's certainly very doable. So I would strongly recommend building those helper routines, as well as using the recursive version of the MINIMAX search. Does that make sense? Any questions? And so I'm not going to enumerate all of them. I'll just mention them. So there's results, there's actions. You give it the state, and you probably give it also the agent index because you need to know which agent is going to play those actions because based on its position, you might not have available all four of the actions, north, south, east, west. And then there's going to be utility. Utility is just going to call the evaluation function, right? And so that evaluation function is your utility function. With that, you're filling in, to go back to the slides, definitions for all these helper routines. And then you're just filling in your recursive implementation inside of that entry point in your get action for your MINIMAX agent. Does that make sense? Right. Any questions? All right. Yes? No, stretching. Okay. Um, so with that, that's all I had to say. Hopefully this is helpful. On Tuesday, we'll pick up with aspects of Minimax search, but we'll spend most of our time on Expect2Max to complete all of the material in support of project number 3. Okay, so do tinker with it. It's kind of, I did tinker with about 8 or so different features, and it's kind of funny to see how these features impact its behavior. But again, don't burn all your time doing that. Move on to the next thing. I'd rather you do that and make forward progress. So if no further questions, any questions going once, going twice? Okay, sold. Have a great weekend, and I'll see you all on Tuesday.